In Module 6, we're going to talk about forwarding inside of the ACI fabric. First, we're going to cover ACI's use of VXLAN, as well as a general overview of the VXLAN technology and how it works. We'll talk about ACI fabric fundamentals, fundamental aspects of the ACI fabric. We'll talk about how packets are forwarded inside of the ACI fabric and how things are learned. And we'll talk about endpoint learning and lookup in terms of endpoints, whether they're virtual machines or physical hosts, as well as ACI fabric innovations. So let's get started.
Before we get to the slides, let's talk about why VXLAN. What's the problem that we're trying to solve? Basically, VXLAN, among other things, is solving two primary problems. One's an old problem, and one's a new problem. The old problem is basically we can sum it up to one particular feature from one particular vendor, and that's vMotion. The ability to provide vMotion access while at the same time doing a more modern CLOS style architecture. So, and the new problem is we are limited in the number of VLANs that we have to about 4,000, give or take, depending on the implementation, which limits our segmentation. So we want to have larger segments. VXLAN actually has a 24-bit address space. So that gives us over 16 million segments to work with, where VLANs is a 12-bit address space and gives us about 4,096 minus some reserved ones. So we get about 4,000. So let's talk about the old problem, and then we'll talk about the new problem. The old problem is a limitation of, there we go. The old problem is a limitation of Ethernet. We've got a couple of things going against us here. One, in Ethernet, we have a simple rule. Ethernet, we can only have one path. That's the whole reason for spanning tree. A lot of people like to hate on spanning tree, but spanning tree isn't the problem. The problem is Ethernet. The golden rule in Ethernet, it's kind of like in the movie Ghostbusters when Egon told the other Ghostbusters, don't cross the streams. We have a similar rule in Ethernet. Never let there be more than one way to get anywhere. Otherwise, we can create a bridging loop. Spanning tree was designed by Ratty Perlman in order to prevent that looping from happening. So what spanning tree does is we designate a bridge somewhere on our network, and it will figure out all the potential paths for Ethernet to go, and then we'll block any redundant paths. It will pick a single path and make sure everything on your network has a single path. So we have just a single path there. The other limitation that we have is we need to be able to support vMotion. We need to be able to support the ability to migrate a VM from one top-of-rack environment to another top-of-rack environment. So what we see here, so vMotion. Now, VMware isn't the only company that does vMotion. KVM, Hyper-V, they both do what they call live migration. It's basically the same thing as vMotion. It's moving a virtual machine from one network to another network without disturbing TCP connections or other connections it might have going on, without disturbing the processes, and without re-IPing. So if this VM here has a IP address of 10.10.0.10, when it vMotions over to this other top-of-rack switch here, 10.10.0.10, it will keep the same IP address. And all the connections will still work and so forth. Won't be interrupted. We might lose a few packets in that vMotion, but for the most part, the VM won't even know anything happened. Another thing, so this network right here, we call this, this will be the core layer up here. We have our aggregation layer, and we have our access layer. Sometimes we will collapse the core and aggregation layer into a single pair of devices, but not always. So if you think about where we put the layer 3, we put the layer 3 up here. So this is our boundary right now between layer 3 and layer 2. Actually, there should be a link in between these two devices that I missed here. Yep. So this is the boundary between layer 2 and layer 3. Our default gateways are sitting on probably on HSRP or VRRP. So we got VRRP. So we've got active standby routers up here typically, acting as our default gateways, and because of that, we're limited to one active forwarder for a given IP address for a given subnet, or at least for a given default gateway. We can't have multiple ones, at least for the same devices, unless you use something like GLPB. But for the most part, we're dealing with one default gateway that exists on one switch. So we're running VRP or HSRP or something like that. Down here, in layer 2, we cannot have multipathing. Now, you noticed here, we've got all of this multipathing here. So we have two choices. The oldest choice would be that spanning tree would run and would block a lot of these ports, would block all the redundant ports, and we get about half our bandwidth. And that's not a good idea. So that's why we typically use something generically called link aggregation. And that's that's an IEEE standard. Aggregation. This is an IEEE standard. It's part of the 802.1ax working group. You may be more familiar with its older group, 802.3ad. And in the Cisco world, in the Catalyst world, we call this Ether channel. In the Nexus world, in the ACI world, we call it, not virtual port channel, we call it port channel. So there's actually a misconception about the difference between Ether channel and port channel. There is no difference. They are both the exact same thing. I can connect a Nexus to a Catalyst, and one side using Ether channel, the other side using port channel, no problem. An individual instance, the generic term is, of course, link aggregation, and an instance of that link aggregation, a single link, is called a link aggregation group, or LAG. So LAG is what we tend to hear in the industry. But in the Cisco realm, we call it Ether channel or port channel, and of course, in ACI, we're dealing with Nexus switches, we will call it port channel. So we're going to use VPC as well. So that's going to. So what? Before we get into that, remember the rule that we had. Quick talk about port channeling. The rule that we had about Ethernet: never let there be more than one way to get somewhere. So if we have these two devices, two network switches, layer 2. So here's our switch 1 and our switch 2. This is two paths. Now, if spanning tree were running, it would block one of these paths. If spanning tree was not running, we would create a bridging loop and quickly overwhelm the network with replicated BUM traffic. So BUM is broadcast, unknown, unicast, multicast. When we do a port channel, what we're doing is we're turning these two links into a single logical link, so that Ethernet and spanning tree in general sees it as a single path. So we're single pathing two paths there. The problem is what happens when I have a single top-of-rack device and I want to connect it to two. I want to dual home it for redundancy, or might be a host. So I want to dual home it. I want to connect it to two switches. If this has just a single MAC address, a single IP address, then this isn't going to work, at least not active-active. This would be active standby. So what we can do is we can use VPC. And what VPC does is turns these two switches and makes them appear to be a single switch from a layer 2 perspective. So we can build a port channel. So this host thinks it's built a port channel to a single device here, even though we have these two switches have two different control planes, but they do share a forwarding plane. So all of this should be fairly familiar to you if you're familiar with layer 2 networking in general. So down here, we've got VPC here, and here, and here, and here. And in fact, these are probably not even that. These are probably back-to-backs. Oops, not quite that, back-to-back. So back-to-back or bow tie. And then from the VMware host to the leaf switches, or to the access switches, these are generally called leaf switches, not access switches, not leaf switches. We're going to build a port channel from this individual host up here. So that helps out a lot with our single path scenario, but doesn't give us the flexibility. For example, I can only build a VPC link to two switches. I can't do it to three. And there's some other limitations there too. But this has got us pretty far. And this is very common. So if in a lot of installations, this will be a bunch of 7Ks, more 7Ks, and then these will be 5Ks, and we'll also have some 2Ks, and maybe some fabric interconnects hanging off there. It's been fairly successful. We could scale this out by scaling out our aggregation layer. We could just build another pod of aggregation layer and hang more access switches off that. And then our core would handle routing to the outside world, to the internet and border routers and so forth. So this is pretty popular. But let's talk about a different type of topology. Now let's take a look at the Kloss style fabric. So this diagram right here, we have, these are the spines, which we talked about in earlier sections, and these are the leaves. I've seen them written as leaves, as in L-E-A-V-E-S. I've also seen them written as leafs, as you see here. I think either way works. So this type of network is called, officially called a Kloss network. So it is not an acronym, so it's not all capitalized. It's actually named after a gentleman by the name of Charles Kloss, and he helped design switching networks for telephone networks in the 1950s. So that's where this particular network came out. So there's a couple differences between this style of network and the older core aggregation and access layer. The first one is that this is a two-tier Kloss, although there can be three-tier Klosses. We have the ability, we've got a couple advantages to this one. One, if we use an Anycast gateway, then our default gateways are everywhere. So in ACI in particular, but other designs too, we have our gateways, our gateways exist on all of the leaves all the time. So our default gateways are local. We don't have to go up to the core in order to start routing packets. We use ECMP between the leaves and the spines. So assuming we have one link between each leaf and each spine, this leaf has 4 paths to get to any other leaf. And we'll divide up traffic using a 5-tuple hash. So we take a look at the MAC address, or we take a look at the IP address headers, we hash them along with the source and destination TCP or UDP port and other header information in order to figure out which outcome we're gonna send. We map that outcome to one of these 4 links. So we're using all links at the same time. Now for layer 3 routing, we don't have that same limitation that we have in Ethernet. We don't have to make sure that there's not more than one path. In ECMP in layer 3, we can have more than one path. And it makes a lot of sense to have more than one path. And we can have more than one path to more than 2 switches together. So in this case, is very simple layer 3. We'll use a routing protocol. ACI uses IS to IS, but we could use OSPF if this were a non-ACI design. So generic Kloss can be OSPF or IS to IS or other routing protocols as well. So we have all links forwarding in a Kloss network. We also traditionally OSPF and other routing protocols have been able to handle failures much quicker than traditional spanning tree, especially. So if we had a link failure here, traditional spanning tree 802.1d would take minutes in best case scenario in order to do a topology change notification and figure out the new paths and start forwarding again. If it was misconfigured, it could take a lot longer. Now, modern spanning tree implementations do this a little quicker, but it's hard to beat routing protocols in terms of reconverging. OSPF can do it in less than a second, and it's very reliable, very well known, or very well trusted, very well understood. So we have the multi-pathing benefit here. We also have the ability to scale out in a couple of different ways. So another advantage is if we need more ports, we can add more leaves. So we can just keep on adding these leaves as many times as we want until we run out of ports on the spines. And if we run out of ports on the spines, then we can just add more spines. We can also add more links in between the leaves and the spines. So we can scale out this architecture in a variety of different ways, which is beneficial. We also have deterministic latency. So we're either local onto a leaf. So if we have 2 hosts, So we're either local on a leaf or we're one hop away. So we know what our we know what our latency is going to be. So we're at the most latent we can have is from one leaf to another leaf going over the spine. We can also tolerate the failure of our spines or many of our spines. We can lose 2 spines. In this case, we could actually lose 3 spines and we'd still have connectivity. We might be a little degraded state because we can't forward as much traffic, but we're typically in a much better position there. So all these are benefits of the CLOS-style network. The problem with the CLOS-style network has been traditionally, though, in fact, it wasn't really a problem until VMware came around. Because when VMware came around, each one of these leaves, or typically pair of leaves, in case we were doing dual homing from the host to those leaves. In this case, we might do this. Oops, erased too many things here. So if we're dual homing, these would be a pair of leaves. We'd have a host here. We would connect up to 2 in a port channel there. But it would still be, that way these 2 switches would be in a layer 2 domain. And they would have a layer 2 connection between them. They'd be doing a traditional VPC. Again, this is not ACI that we're talking about. This is just generic CLOS networks. But the problem is, if we wanted to get from this pair to other leaves, we had to cross a layer 3 boundary. So that meant we couldn't have this host. So let's say its network was 10, 100, 10, 10. 10, 100, 10, 10 only exists as a subnet on the default gateway, for example, on this pair of leaves in a traditional CLOS network. So we could not vMotion over onto this one because this network might be 10.101, 10.0/24. So if we had to vMotion over to this rack here, then the host would not have any connectivity or would have to re-IP, or the VM. So this is a VM issue. So if we had to do that, then until VMware came around, this wasn't a really big deal. In fact, in the mid-2000s, we started to see a lot of these networks being built, especially as we got the multi-layer switches. Multi-layer switches being switches that could route as fast as they could switch, or at least you could do significant amounts of routing in addition to just layer 2 switching. So we started seeing a lot of these networks being built in the effort to get rid of spanning tree and to get rid of the limitations that we had with non-multipath Ethernet. And then VMware came around, and we had to abandon this pretty much and go back to our core aggregation access layer. So one of the problems that VXLAN solves is the ability to have this type of CLOS network with all its advantages and still be able to provide the vMotion capability that we need for modern data centers. So what it does is we provide, VXLAN creates an overlay network or multiple overlay networks on top of your existing network. So everything in red, it would be considered the underlay. So we wouldn't put our VMs on the underlay network, we would put them on the overlay. So VXLAN network. VXLANs have VNIs, virtual network identifiers, or VNIDs. And these are like VLAN IDs. So the VNID address space is 2 to the 24th power, so over 16 million addresses that we have available to us. And as opposed to the 4,000 or so we get with VLANs. So let's say this is VLAN segment 100,001. Then we would give it a network, so maybe 10, let's do 50.0.1. We could put an Anycast gateway on there depending on the implementation. So our VM could sit on a host over here, and it could have an IP address of 10.50.0.10. And then we could vMotion from this rack to this rack. Now, the underlay network, each of these racks is on a different layer 3 network. So we'd have to cross a layer 3 boundary in order to do that vMotion, except the fact that we are on a VXLAN overlay. So this would allow us to migrate 10.50.0.10 over to this rack, and our default gateway would still be there. And that would allow us to have the best of both worlds. We can have our leaf spine CLOS network with all the advantages, and we can still provide vMotion capability. So that's how VXLAN solves one of the problems that we're facing. Let's talk about how we're solving the other one. So we talked about VLANs give us about 4,000. So this is roughly 4,000 segments that we can have. So we might call this macro segmentation. A lot of organizations will have their network separated into VLAN. So this is VLAN 10. This is VLAN 20. This will be VLAN 30. Now VLAN 10 is going to be our DMZ. So what do I mean by macro segmentation? I mean that we are putting hosts onto this DMZ that are very loosely related. In fact, the only way that they're related is the fact that they need access from the outside world to come in. So we probably got some sort of firewall. Make that a more legible F there. Firewall. And a connection to the outside world. This firewall is protecting this DMZ VLAN here. And we put it all on this similar network, these VMs on the similar network, because they all need inbound access and they need to be protected by that firewall. Then we'll put VMs in the other segments. Maybe this is our application layer. Maybe the other VLAN's a corporate layer, so maybe this is just physical hosts, not virtualized hosts. And then we'll do inter VLAN routing, IVRs, or SVIs, and inter VLAN routing. Maybe we'll put even firewalls in between them. Depends on how much we want to put firewalls in the way there. So we're grouping virtual machines and physical hosts. We're grouping endpoints together in very loose ways, or not loose ways, but we're making very large groups here, and they're only very slightly related. What we can do with, and part of the reason why we do this is twofold. One is because we don't have that many VLANs. So let's say these two VMs are related, these two VMs are related, these three VMs are related, these two VMs are related into their own applications. We could do something like private VLANs and put them and group them together and put them into their own network segment. Let's pick another color here. So maybe we can put them into their own segment here. So this DMZ VLAN 10 would be the primary VLAN, and each one of these would be a secondary VLAN. We could do that. There's two things kind of preventing us from doing that. One, it requires a lot of coordination because these secondary VLANs need to exist on every switch in a given topology. And sometimes it's difficult operationally to make sure that we've got the same VLANs on every switch, and we can run into troubleshooting issues with that. Another issue is that we just probably don't have enough VLANs to burn. Especially if we have an organization that's got a couple hundred applications and we quickly run out of VLANs. So with VXLAN, we get that 16 million. So VXLAN gives us 16 million potential segments. And we're not going to run out anytime soon. Other technologies can help us out with that coordination. So, for example, ACI, which uses VXLAN, also uses a high degree of orchestration so that we can, we actually have an effect very similar to VXLAN, or to private VLANs rather, with bridge domains and EPGs. But we can shrink our segments so that only directly related endpoints are in a given network segment. And then we can control how the different network segments can talk to each other. Or at least we have the tools that can allow us to do so. And when we talk about VXLAN, there's one thing I want to make clear here. We're really talking about two different types of VXLAN and ACI. Inside of the ACI fabric, we have a modified version of VXLAN. So VXLAN has some reserved headers for future use, and Cisco makes use of that header space in order to do some of the innovations they needed to do in the forwarding plane. So inside of ACI, we call it either eVXLAN, extended VXLAN, or the older term was iVXLAN. But inside of the ACI fabric, this is a non-IETF standard implementation of VXLAN. Now, don't let that scare you. Just because we're using inside of the fabric a non-standardized version of VXLAN doesn't mean that we can't communicate with VXLAN to the outside world. So let's say we're using standard VXLAN out here. So this is IETF standardized VXLAN. Packets can enter in the ACI fabric. The outer VXLAN, or sometimes in ACI we refer to this as outer VXLAN, but outer VXLAN is just an ACI term to disambiguate from interior VXLAN. This is the demarcation point. At this point, a VXLAN packet would be decapsulated. The original interior Ethernet frame and its IP packet inside would be preserved, and then we would add in the interior or eVXLAN header. So it traverses the fabric as Cisco VXLAN and then can leave. So we decapsulate from the eVXLAN header, and then we can do things like encapsulate in 802.1q. So just a regular VLAN header. So we can normalize between different types of encapsulations. We can take VXLAN, which is a standard encapsulation, and we can forward traffic and re-encapsulate into VLAN, which is also a standardized implementation. So this is governed by the IEEE, of course. So there are two different types of VXLAN which we're going to be talking about. The rest of this module is going to concentrate on the Cisco implementation of VXLAN, the eVXLAN. But again, just because we run a non-standard version inside of the fabric doesn't mean we can't communicate with standardized VXLAN outside of the fabric. Think of it think of ACI as a chassis switch. If you take a chassis switch from any vendor, it's got line cards that you can only use with that vendor. That's true for just about every vendor. Also, inside of any switch is an interior encapsulation that you just never see. For example, with the Broadcom-based switches, we use an encapsulation called High-Gig 2. That's true for Cisco, and it's true for other vendors as well. So there's additional header information on there to get the packets forwarded inside of the chassis itself, whatever the internals are. And that header is stripped before it ever leaves the switch, so we never see it. So that's true with the eVXLAN inside of ACI. So while it's non-standard inside, we speak standard encapsulations and standard encapsulations and segmentation outside. So VLAN, VXLAN, Ethernet, and IP. All right, so again, just a quick overview of what we talked about. VXLAN extends layer 2 connectivity across a layer 3 boundary, provides integration between VXLAN and non-VXLAN infrastructures, so we can encapsulate, decapsulate. We have a higher scalability than VLANs, up to 16 million VXLAN segments. We utilize all available paths, so no spanning tree blocking. We use ECMP. And we can have more than 2 core switches, or in case they'll be called spines. And the Nexus 9000 series switches provide hardware-based VXLAN functions. So that includes also VXLAN routing, which is something that the standard Broadcom Tomahawks and Trident 2s cannot do. So this is a VXLAN packet format. This is the Cisco version of the of VXLAN. So this is the eVXLAN or interior VXLAN. It is an 8-byte header, so 64 bits. The VXLAN ID itself is 24 of those bits. We require a 50-byte overhead because not only are we doing the VXLAN header, we're also throwing on an extra UDP header, IP header, possibly 802.1q header, and source and destination MAC address. So all of this together can add up to an extra 50 bytes of overhead. So you need to make sure if you're running VXLAN that you've got your MTU bumped up so you can support this. Most switching platforms that run VXLAN can support up to 9216 for an MTU, which is, and then the host-based MTU tends to be around 9,000 bytes. So that should provide plenty of overhead that we can do VXLAN encapsulation and any other encapsulation we might have to throw onto the wire. So on the right here we have the original Ethernet packet. We've got the VXLAN ID, UDP. So VXLAN is Ethernet in UDP. So we have a UDP datagram. We've got some extra headers for VXLAN. We've got the IP header and then possibly another MAC header. So let's take a look at the VXLAN ID itself, or the VXLAN header itself. It's 8 bytes. The first byte are the Lisp flags. Second byte are the flags DRE. Then we've got the source group or class ID. Then we've got the VXLAN instance ID. This is part of standardized VXLAN. And then we've got MLBSP. So what do these mean? Well, first of all, VXLAN, so ACM maps the network context into the VNID, so the VXLAN ID. So colloquially, we call it VXLAN ID or just the VXLAN. The official term is VNID, or VXLAN Network Identifier. So the ACI maps the network context to the VNID. So tenant traffic that it was sourced from, the VRF if the packet's to be routed, bridge domain if the packet is to be switched, and then the EPG for the service graph if the packet is to be redirected. So what do these extra headers here mean? So we've got flags DRE. LB indicates the discounting rate estimator for load balancing and use, which we'll talk about a little bit later. DL indicates destination TEP should not learn the source TEP to NRIP binding. So there are cases, not many cases, but there are cases when we just don't want to install a new forwarding entry into the destination leaf. So this is just a good way to say, hey, here's a packet, but don't worry about learning the address. E indicates the frame has experienced a forwarding exception, so fast rerouting or a bounce. So we'll talk about how that might happen. For example, a vMotion. SP indicates the source policy has been applied, so we try to apply policy. So that's our forwarding policy based on the source EPG. But sometimes we're not able to do that, and then DP indicates that we've applied it at the destination. DRE is used to indicate extended path load, but only if the LB bit is set, and we'll talk about that a little bit later. And then MCAS indicates if multicast frame is to be bridge or routed and the original encapsulation. From the source group, source group is the identifier indicating which EPG policy the frames belong to. So this will be the class ID. So if you ever take a look at an EPG, you'll see a class ID. That's what it maps to here, or one of the things that it'll map to. The next set of flags after the VXLAN ID, M indicates which bank of atomic counters should be used for this packet. So this is a Cisco specialization. LB tag indicates which LB tag the LB feedback is for, which group. LB metric indicates congestion metric for the specified LB tag. And then S port indicates the original source port. So we'll talk about all these things a little bit later in this lesson. So VTEPs originate and terminate VXLAN tunnels. One of the primary components in VXLAN is the concept of the VTEP. VTEP is where packets come in, either VXLAN or non-VXLAN, get encapsulated or decapsulated, and then forwarded via normal means, or traditional means rather. So each VTEP has two interfaces. The switch interface, that's on the local LAN segment. So that's the one doing accepting packets and frames that are non-VXLAN encapsulated. And then the IP interface, the infrastructure LAN, with the following functions. So the IP interface uniquely identifies the VTEP on the transport network, encapsulates and decapsulates VXLAN frames, discovers remote VTEPs for its configured VXLAN segments. So we need to make sure we know we have a mapping of where the destination VTEP addresses are. And learns remote MAC address to VTEP mappings, similar to a CAM table inside of a traditional switch. Or whether or not that CAM table learns MAC addresses or /32 or /128 host routes. So the fabric addressing, where do we get these TEP addresses? Remember, we created these TEP pools. So that was enter the address pool for TEP addresses. That's what we're assigning here. So the leafs all get TEP addresses. They're /32, and ISIS is what's responsible for routing them. The spines also get VTEP addresses, and there's a reason why they have TEP addresses. They don't typically do a lot of encapsulation or decapsulation, but they do have the station table. They do have the global proxy table, or the proxy table rather, and we'll talk about why that's important. So fabric fundamentals. ACI, like I mentioned before, does encapsulation normalization. So the idea is that we want ACI to be able to handle multiple types of encapsulations, because the types of encapsulations that we're dealing with on the network are increasing. So it used to be, for 20 years or so, or about there, we would deal with VLAN encapsulation as our primary method of encapsulation. Now we've got VXLAN and possibly NVGRE, and whatever else might happen in the future, we're going to normalize that. So we can take a packet that is sourced from a VXLAN encapsulation, and we can deliver it to another VXLAN. We can actually route the VXLAN as well. Again, something that a lot of the hardware chips can't do, but ACI can. We can also take VLAN packets and forward them onto NVGRE, or NVGRE to VXLAN, or VLAN to VXLAN, etc. So we can take regular Ethernet, we can take IP, we can take 802.1q or VLAN tags, VXLAN, and NVGRE. Anything can come in and anything can go out. Inside of the ACI fabric, as I mentioned before, this is the Cisco-specific version of VXLAN. So even if we use VXLAN on the outside, it's going to get mapped into an interior VXLAN, and then when we forward it out of a leaf, it'll get encapsulated into possibly another the same external VXLAN or a different VXLAN ID, but it is normalized. One of the other things we do with the ACI fabric is we decouple identity and location. So an IP address we consider that identity. Location has often been, at least in the early 2000s and late 1990s, location has been determined by where you place that workload. So which rack, what top of rack, what switch you plug it into. By decoupling identity and location, that's essentially what we're doing with vMotion. So if we want to be able to support vMotion, we can move a VM from one part of our network to another part of our network without removing or without re-IPing and without disturbing inbound TCP or other connections. So that's so mapping internal tenant MAC addresses to location is performed by the VTEP using distributing mapping database in the spines, and we'll talk about what that means. So how do we forward traffic in the fabric? So leaf packet flow. On the ingress, as packets enter in a leaf, we derive the EPG, typically, usually, not always, but usually by the source VLAN ID. We do a station lookup. We do a policy lookup. We do an NCAP onto the interior VXLAN, and we might even perform a bounce. On egress, we'll do the VXLAN termination, so we'll strip the interior VXLAN header off. We'll do a station lookup, a policy lookup, and then the egress port selection. So if we're going to send traffic from this virtual machine to that virtual machine, the VTEP might be cached on the leaf. If so the IP address or the MAC address of this virtual machine here is already known on the leaf, so we need to look up locally, and then the spine just forwards it along. If we have a packet or a frame that needs to go to a VM and we don't know where to send it, the VTEP will forward it to the spine. The spines know all. The spines know where everything is. The spine will do the lookup, and then if it finds the entry, then we'll send it to the appropriate leaf. So functions supported by the ACI spine, we are transit, IP forwarding to traffic between VTEPs. If it's transit, that means we don't have to do a lookup. We can just forward the packet. We can do a proxy lookup, so the data plane base directory for forwarding traffic based on mapping a database of EID and VTEP bindings, so endpoint ID. So while the leaves do not learn all of the addresses, the spines do. The spines know where everything is. So if you don't know where something is, you send it to the spine, and the spine will make sure it gets forwarded to the correct place. Multicast route, so the ACI spines we can divide up to 16 multicast forwarding topologies between the spines. Although not all functions are required on all spine switches, transit and proxy lookups are. So we have one thing to keep in mind: ACI is purely hardware forwarded. Nothing gets sent to a CPU. So some other SCN solutions might, for the first couple packets, you might have to install a flow. So that means you send it to a flow lookup database, and that's done in software, and that can really slow things down. In ACI, everything is done in hardware. So leaf forwarding table, we got basically 3 different tables that we're dealing with here. One is the local station table. Second one is the global station table, and both of these are on the leaf. Then on the spines, we have a proxy station table. So local station table contains addresses of all hosts directly attached to the leaf. So the leaf will know all that is connected. So virtual machines that attach via hypervisors and are learned through LLDP, for example, will know those addresses. Physical hosts, when you plug them in, so we'll learn those addresses. We'll learn IP addresses or MAC addresses depending on whether or not we're doing layer 2, layer 3 forwarding on the bridge domain. The global table is a place where we learn addresses and where to send them to that are not directly connected, so something that will be on a remote leaf. Now, we're not required to learn everything. We might cache some entries. We might cache a bunch of entries, but we're not required to learn anything, because if we don't know an answer, then we will send it to the proxy. So we have a kind of a default route here. So if we don't know, if it's not local and we don't have it in the global station database, then we're going to forward it to the proxy. The proxy has the proxy station table, and that has everything. The proxy station table is replicated across all spines. So all spines have all information. And this is part of the Council of Oracle's protocols, COOP. So Council of Oracle's protocol, it's a very simple protocol. It has 2 lines in the actual protocol definition. 1, if you're a citizen in ACI, the leaves are considered citizens. Citizens are not required to know anything, know everything rather. So citizens are not required to know everything. Leafs are not required to know everything, but they are required to, if they learn something, they tell an oracle. So that's line number 1. If you're a citizen and you learn something, you tell an oracle. Line number 2 is, if you're an oracle, you tell the other oracles. So that means the oracles know all, and they share information. So if they learn something from a leaf, so for example, this leaf here learns something, all it has to do is tell one oracle. It doesn't have to tell them all. So it tells one oracle, and the oracles, and this oracle will tell the others. So what we end up here is the forwarding table is installed on every spine. That's part of what makes a spine special. They're built in such a way that they have the large forwarding tables necessary in order to handle all these entries. With the leaves, we can use less expensive chips and less TCAM space, less forwarding table space. Because forwarding table space is a premium. It has a cost associated to it, and by distributing our database, so to the database concepts we may have talked about before, sharding and distribution. We're sharding our forwarding table across all the leaves. So we're taking a workload, splitting it up across all the leaves. So not all the leaves have to have every entry programmed into them. In traditional layer 2 networking, every switch on a given VLAN needs to know every MAC address on that VLAN. And that can run into some scalability issues. Here, we don't have to have that. The proxies do need to learn everything, and so they have the additional hardware forwarding space for that. So let's do a walkthrough real quick. So we've got 2 virtual machines attached. One is attached either through a vSwitch or some other, or maybe it's just a direct host. It says a VM here, but maybe it's a physical host. So either way, we attach these 2 devices, 10.1.3.11, 10.1.3.36. So let's assume for argument's sake that they're on the same subnet. Maybe it's a /24. So the local station table for leaf number 1, so we're looking at leaf number 1 here. The local station table is 10.1.31 on port 9. So now we know where to find that. Any packet destined for 10.1.3.11, we'll forward it out to port 9. The global station table, we just have the default route for proxy in case we get a packet to forward that we don't know what to do with. So you'll also notice that the global station table, or I'm sorry, the proxy station table has the entries for both VMs. And now we've got these two VMs, and maybe this is a bridge domain that is not doing layer 3 forwarding. So we do not have the unicast routing box checked. So we're just doing forwarding based on MAC address. So the proxy station table knows about all 4 systems here. So we've got 2 VMs here, then we get 2 VMs here. The proxy station table, or the spines, are responsible for learning all of them. And on the local station table, in the global station table, we've only learned the direct detached. So let's say 10.1.3.36 sends a packet to 10.1.3.11. So now we're going to put an entry in the global station table, so 10.1.3.36, and we can send that to leaf 2. So a packet, so we've learned this, so a packet comes in, we learn it, we send it to the global station table. We program it into the global station table. So now when we source a packet from 10.1.3.11, it's going to be sent to 10.1.3.36, and we'll send it to leaf 2. So notice we don't send it to leaf 2 on a given port, we just send it to leaf 2. And what do we mean by leaf 2? We mean the VTEP address. So that's that was assigned from the TEP pool. So the IP packet, so the packet gets, or the frame, or in this case it'll be the packet gets encapsulated into a VXLAN header, and the destination IP address for that VXLAN segment is leaf 2. So the packet will get forwarded there. If the VM here sends a frame to 10.1.3.11, sends it to this leaf, then we'll install the MAC address in the local station table. So anything with this MAC destined to this MAC address, we just forward it on to leaf 5. The packet gets to leaf 5, then leaf 5 will have the local station table, so it'll know what port to forward it out of. So one of the things that we do in ACI is we have a distributed default gateway. So all leaves have the SVI, or any cast address, has the SVI for all segments upon which they have installed VRFs and or tenants. So for example, if this were part of tenant Coke, we would have the SVI for this bridge domain installed onto this leaf. If we not have any Coke tenant, any ports configured for Coke on this leaf, we would not install that SVI. We would not install any forwarding entries, and that's sharding our forwarding table again. So Fabric provides pervasive SVI for all leafs that need it, forwards layer 2 and layer 3 connectivity directly to the destination endpoint. The Fabric learns a MAC for non-IP packets, or for not doing unicast routing, and then we learn IP addresses for all their packets. So we can learn either one. All right, let's do a little packet walk between these 2 virtual machines here. So we've got 2 virtual machines. One's plugged into a VMware vSwitch, and one's plugged into a Microsoft vSwitch for Hyper-V. That doesn't really matter which is which. Now, when a packet leaves a virtual machine, it's typically encapsulated into Ethernet, and no other encapsulations are done. So this is a naked Ethernet frame with an IP packet encapsulated inside. So pretty typical, untagged, unencapsulated. So the vSwitch is going to be configured to do, typically we'll do some sort of encapsulation, whether that's VXLAN or 802.1q or VLAN tagging. In this case, we're going to say we're going to do a standardized VXLAN encapsulation. So when the packet leaves this VMware vSwitch, it's going to be encapsulated into a VXLAN packet. Now again, this is standard VXLAN or outer VXLAN. When it hits the leaf, we're going to strip that VXLAN header off, and we're going to put in the interior VXLAN header, the eVXLAN, that's unique to ACI. It adds a couple extra fields into the packet headers to do the forwarding. If the leaf has learned the inner IP to egress VTEP binding, so that's this IP address to this VTEP binding, if it knows it, it will send it directly. It will craft a packet that's directly destined for that VTEP of the leaf of this leaf right here, of the egress leaf. If it doesn't know it, it will forward it. If it does not know, it will forward it to the spine, to the proxy. And the proxy will know where it is. If the proxy doesn't know where it is, it's either going to flood it or drop it, depending on how we configure the bridge domain. Now, there is an Anycast VTEP. So each of these spines has the same VTEP address. So they all have their own VTEP address, but we have an Anycast VTEP address for all of the spines, so that we have an equal cost multipathing going from the leaf to the spines. So this VTEP could send this packet to any of these spines. And since all the spines know all the information, know all the addresses and destinations, it doesn't matter which spine we send it to. We can distribute the load to them. The egress leaf will swap the outer VXLAN with the correct egress encapsulation. So we'll pull off the interior VXLAN, and then we'll encapsulate it into, in this case, it'll be VLAN. Send it to the Microsoft vSwitch, and then the vSwitch will pull off that encapsulation and deliver the packet as an unencapsulated standard IP packet. So what happens if we do a vMotion? So if we do a vMotion from one leaf to another leaf, there's going to be a period of time where we're going to have packets still hitting the old egress leaf. So the first thing we need to do is we need to make sure that everyone knows that this virtual machine 10632 is on a new leaf. So the way that we do that is either through a unicast GARP, gratuitous ARP, or a RARP. The difference between a GARP and a RARP is a RARP, we don't have to know the IP address. We may not have learned the IP address yet, but a RARP will have the MAC address. RARP is mostly ignored by endpoints, but it is useful because RARP will be, the switches will pay attention to it. So we could either do GARP or RARP. On notification of an endpoint move, once we've learned that an endpoint is moved, the GARP or RARP will source from the vSwitch endpoint. The leaf will send an update via the COOP, the Council of Oracles protocol, to the spine. And the spine will then send it to the other ones. We'll also simultaneously send a bounce entry to the old leaf. Now the bounce entry tells the old leaf, this address was once here, but it's now located on a different different leaf. So we can forward the packets over. So bounce frames are marked with an exception bit in the VXLAN headers, so that helps us prevent redirect looping. The ingress leaf will continue to forward packets to the egress leaf until we've received the update. So we might send it to the old leaf, but the old leaf has the bounce entry, so it'll get forwarded up into the correct leaf. And then eventually, and I say eventually, this happens within a second or two, all of the proxy tables will be updated on the leaves, and on spines rather, and the leaves will have their entries updated as well. So this should minimize any packet loss when doing vMotion. So each leaf has multiple equal cost routes to all other leaves across all octave paths. So this particular leaf has 4 distinct paths to any of the other leaves. Should we lose a link, which can happen, the leaf node removes the entry for that link, and the hardware hashes subsequent frames across remaining paths. So we reassign the buckets, or we reassign the path. So hardware can detect link failure and updates, and it will update the forwarding entries in about 125 microseconds. So that's an extremely fast rerouting of packets. There should be very, very minimal packet drops here. The spine will forward traffic to any remaining leaves on detection of direct path loss at the target TEP. So leaf will forward along any valid paths. IS to IS will eventually move the route to spine with the failed down leak, and we will, and IS to S will also reconverge on the new routing information. So multicast forwarding, spine switches maintain a table of GIPO multicast IP overlay groups to leaf binding. So a leaf will receive a traffic for a GIPO in the if the EPG bridge domain exists on that leaf, and the GIO represents a multicast TEP. So if we have multicast frame is received from a server to the leaf, so the leaf gets that multicast frame, and it's attached to a unique EPG bridge domain on either a VXLAN, VLAN, or NVGRE segment or port. If it's local, then it is replicated locally. So if we have a multicast subscriber on that leaf, the packets will go locally, of course. If it's on a remote TEP, the ingress leave maps the multicast group to a GIPO, and a hash is flowed to the FTAG tree, forwards the packet across the spine. The spine will replicate and forward the frame to the leafs based on that GIPO address. So it will send it to whoever needs to get it, whichever leaves are part of that multicast group, and then the local leaf will then replicate further downstream. So we only replicate where we need to replicate. And the multicast frame is received with the headers pulled off. So how do we learn these endpoints? So everything in ACI is learned. So we have a couple ways to do tenant endpoint learning. One, data plane learning creates mapping to the leaf. The DHC forwarding can be used to learn the entry. ARP, GARP, and RARP we can use that. We can use VMMs, virtual machine managers such as vCenter. And the APIC, we can also statically program in entries as well if we need to in certain situations. So the Council of Oracles protocol is used to communicate the location and identity mapping to the spine proxy, and the spine will then replicate from there to the other spines. Okay, so let's talk about ACI multicast forwarding. So we run an underlay network for multicast like we run an underlay network for unicast, so that we can have multi-tenancy. For example, we might have two tenants that use the same multicast group. So there's an overlay there's an underlay for that as well. So we run a multicast IP overlay group, and we bind those to leaves. There are FTAG routes for each up to 16, so 0 through 15, and we'll split them out across however many spines you have. So in this case, we have 4 spines, so we have 4 per spine. So the way the traffic works is that, let's say a multicast packet leaves a host, it's got its payload, it goes up to a leaf. If traffic is directly attached, so if we got a host on the same bridge domain, and it's directly attached, then we'll switch it locally or forward it locally. If we have to go to a remote leaf, we encapsulate the packet into a VXLAN packet with the GIPO as the destination address. The packet will go to the associated spine, and the spine will then, so we'll unicast, well, not really unicast, but we'll send a single packet up to the spine. The spine will then replicate and send to whatever leaves that need to be sent. Then the leaf will then take that packet, pull off the VXLAN header, and deliver it locally to the local switch ports. So the multicast frame is received from a server within the attached to the unique EPG bridge domain. So we replicate locally, or replicate on the egress leaf. Now let's talk about endpoint learning and lookup. So there's a couple of different ways that the ACI fabric can learn the endpoints, the MAC addresses and IP addresses, or both of endpoints. We can learn through data plane, so the traffic is flowing through the leaf. We can learn through DHCP forwarding. We can learn through ARP, GARP, or RARP. As these devices do these gratuitous ARPs or ARPs, we can learn the location and identity that way. We can learn through VMM updates as well as VMM creation. So, for example, vCenter creates a virtual machine. It's going to inform the APIC that a new virtual machine has been created and give it its MAC address and probably its IP address if we have VMware tools installed. And then we can also statically program in locations. So you can actually put in the IP address and MAC address as well as the destination port. If you need to do something statically, for example, if you have a silent host, a host that doesn't do ARP, GARP, doesn't have VMware tools installed, or otherwise is not going to let the fabric know that it exists, we can statically program it in so that frames and packets can still reach that destination. And COOP, the Council of Oracles protocol, is used to communicate all of this location and identity. So identity being IP address and MAC address, and location being destination port. And we'll report this to the spine proxy, and then the spine will report it to the other spines. So let's take a look at a learning example here. So a packet gets sent by a VM. When the packet leaves the VM, it's almost always just a naked Ethernet frame with an IP packet inside. So VMs, again, typically don't do 802.1q encapsulations or any type of encapsulations. That's up to the vSwitch. The vSwitch can encapsulate it into, may or may not, depending on the vSwitch and how it's configured. But it usually will at least encapsulate into VLAN, or in this case, VXLAN. The leaf will take that packet. The leaf learns the IP and MAC address and ingress port and incap, it's encapsulation, and that becomes programmed into the APIC. The leaf will inform one of the spines, doesn't matter which. It uses an anycast address, then ECMP will get it to that anycast address, and so it'll report to one of the spines. The spines will then replicate that to the other spines so that everyone has the same, all the spines will always have the same information. The egress leaf learns the internal IPMAC, caches the source VTEP address, forwards it to the vSwitch, and the vSwitch will forwards it using an encap of 802.1q in this case, and will transmit the packet to the VM. So the ACI VXLAN header, so this is the internal VXLAN header, or eVXLAN for enhanced VXLAN, has a couple extra fields that we use. One is the source group, and that's used as a tag label, identifies the specific endpoint for each EPG. And then policy is enforced either on ingress, usually, or egress. We can do that as well. As part of the flags part of the header, we have SP and DP. SP indicates the source policy has been applied. DP indicates the destination policy has been applied. So policy can be enforced at source or destination. And then the source group EPG. If you take a look at an EPG, if you look at the settings, you'll see a class ID. So that's what gets populated into that header. So enforcement example. So a packet gets sent from a VM, and the EPG is derived from the ingress classification. Typically, that means VLAN or port group in VMware, which is mapped to a VLAN, but it could also be a physical port, could be IP address, could be VLAN, could be an attribute of the VM itself, depending on how it's configured. Packet, the vSwitch encapsulates the packet. In this case, we're going to do VXLAN. The ingress leaf populates the source group based on a classification. So whatever class ID we have for that EPG, that's going to get inserted into the source group header. And then we'll do this SP policy bit set, so that would indicate in this case that we have policy has been invoked and we've applied that policy. The packet gets forwarded. If the SP flag is set to 0, the egress leaf sets the DP bit policy and enforces policy on egress. And then we forward the frame to the local vSwitch. In this case, we're forwarding it down to the Microsoft virtual switch under 802.1q, and then the Microsoft virtual switch strips that header and forwards it to the VM. We can check out client endpoints. We can go to the EPG operational tab, and we can verify that endpoints are learned, including the path, so what interface it's being learned on, and the encap. And then we can go to fabric and topology and global endpoints, and we can actually take a look at what the global proxy table looks like. So this is all of the endpoints that have been learned by the ACI fabric. So this is everything that's been programmed into the global station, into the spines, that is. It also includes the source interfaces and MAC addresses and IP addresses if we've learned them. And especially when you get a really large fabric, there's going to be a lot of IP addresses, a lot of MAC addresses. So you can click on the particular field and go down and get filters, and then you can type in a MAC address or part of a MAC address or part of an IP address, and you can filter the results. So there's a couple fabric innovations that we do in ACI. These are things that Cisco has done to enhance the forwarding capability of the ACI fabric to make things a little bit more efficient. For example, we do hardware-based directed ARP forwarding. So this is kind of like unicast ARP or directed multicast or directed broadcast. So if a device does an ARP, so it needs to learn the MAC address of a host on its broadcast domain, on its bridge domain, it will typically do an ARP, and that ARP will get replicated. That ARP will be received by all the layer 2 switches, and will be replicated and forwarded out all ports that are set for that VLAN. That can involve a lot of broadcast traffic. Every host on that broadcast domain is going to have to receive that ARP, look at it, evaluate it, and realize it's, most of them are not the proper destination, so they ignore it, but they do have to spend CPU time evaluating it. So that's one of the reasons why we tend to shrink our broadcast domains and limit them to no more than 200 hosts or so. Modern CPUs can probably handle a lot more in terms of broadcast, but best practice is we still reduce that broadcast domain. In ACI, we already know where everything is. So rather than go through the process of replicating and forwarding that broadcast to all ports, on ingress, so when the ARP packet leaves the endpoint, we can, at the leaf, the hardware can actually evaluate and look up what the destination is. So we'll take that broadcast frame and we will forward it in a unicast manner to that host. So, for example, if this virtual machine were 1.1.1.1 and we did a who has 1.1.1.1, chances are we know where that is already. So we don't have to broadcast it everywhere. We can forward it directly to that host. The host will respond. And rather than have a huge broadcast, we're just doing basically unicast or unicast-like. So that way we don't have to flood traffic. The Leaf ASICs can forward GARP to Leaf where the VM was originally attached. So when we do a vMotion, very common, the GARP source, when we get a GARP or RARP from that VM, the Leaf will then on behalf of the fabric, we'll then install a bounce instruction, so a bounce entry into the TCAM, so that traffic that is still destined for that split amount of time. So when we do this vMotion, the fabric's going to be in an inconsistent state for a small amount of time for forwarding traffic for that MAC address or IP address. And this is true for all networks. Whenever you do vMotion, all of a sudden that VM ends up on a different port. You have to ARP, it has to propagate, and it will take some time. Now, typically less than a second or two, but one of the things we can do to minimize the number of packets lost is that when that vMotion occurs, the leaf receives that ARP or that GARP or RARP. We'll then install a bounce forwarding entry into the old leaf, so that if traffic hits that old leaf because this particular spine has not been updated with information, or this leaf has not been updated with that information yet, may take a little while for it to propagate. Again, typically less than a second or two. It'll hit the leaf, and rather than get dropped, it'll get bounced again and forwarded to the correct leaf. And then eventually, the leaf will have informed the Oracle, and the Oracle will have synced up its database with all the other spines, and then we can get rid of that bounce entry. Another cool innovation that we'd have in ACI is something called flowlet switching. Now, this is not turned on by default. It is turned off. You can turn it on, but you must have NTP at least. You can do aggressive mode and PTP, but you must have NTP at least. So normally we have ECMP going on. So we do a 5-tuple hash of the packets leaving leaf 1 and arriving on leaf 3. And depending on the hash bucket, traffic will get directed over one of these paths. Well, ACIs since we're looking at the underlay and the overlay, we can take a look at the congestion, or take a look at the utilization in each link. And if we see some imbalances, if we have flowlet switching turned on, we can redirect packets to a different path in order to balance out the links. Now, the issue here, if you go back to one of our earlier lessons, we talk about one of the cardinal rules of forwarding on any kind of network, on any kind of IP network. And one of those rules is thou shalt not deliver out of order. So we want to minimize any chance of an end host receiving packets out of order. Now, it's going to happen if you drop a segment or a TCP segment, we have to redeliver it, and that means it arrives out of order. But that involves a lot of work for the host, so we want to avoid that whenever possible. So switches, that's the reason why we do hashes instead of per packet load balancing. So we need a deterministic path so that way we don't ever have anything end up out of order. So flow switching takes advantage of the fact that we have deterministic latency. So if we have a gap, and since TCP traffic is typically bursty, if a given flow is silent for the amount of latency we have between leaf 1 and leaf 3, then we can actually dynamically switch the direction of that flow, switch its hash bucket. And by doing that, we can rebalance the flow without delivering any out-of-order packets. Now, that gap needs to be larger than the latency between those two links, but since we're running atomic counters, we can take a look at those latency and determine, all right, we have a slowdown, we have a silence in this flow. Let's go ahead and switch it over. And this is developed by Kandula et al. in 2004, so this is about a 12-year-old idea finally being implemented. Another innovation is the concept of dynamic flow prioritization. So real traffic is typically a mix of elephant flows and mice flows. And the problem with that is that the mice flows are typically far more latency sensitive and performance sensitive to drops and to latency than the elephant flows. So a mouse flow might be like a quick update, or an iSCSI read or iSCSI write, where an elephant flow might be vMotion. And for an elephant flow, it typically doesn't matter if a transfer takes 20 seconds or takes 23 seconds. So if we drop a few packets, we have to do retransmits. It's going to add on to the time of that flow. But like backups, vMotions, long transfers typically are not adversely affected by dropping a few packets and the additional latency of being put deeper into a queue. Whereas a mice flow is going to be far more sensitive to those type of things. If we only have 10 packets in a flow and we drop 2 of them, then we're going to have a much more impactful drop than if we have 1 million packets in a flow and we drop 20 of them. So one of the things that we can do is we turn on dynamic flow prioritization. Again, this is not turned on by default. It's also mutually exclusive to to flowlet switching. So what we can do is the fabric can detect, so it's taking a look at the traffic, it's looking for patterns, and it will detect flowlets in smaller flows and then put them higher in the priority. It will serialize them out. This is somewhat akin to like a priority queue. So especially if you have voice traffic, you want to get that delivered as much as you can. So you're going to put it in a priority queue, and priority queues always get serviced first. So this isn't quite that extreme. So we're not servicing all smaller flows first, but we are putting them ahead of the elephant flows. So this can end up with much better throughput and much better latency for the quick action flows, while sacrificing a little bit of the elephant flows, having them be dropped more often, being serialized later. But again, those type of flows are usually not nearly that sensitive to drops and serialization and latency. So that's something you can turn on. Again, it is not turned on by default.